So let's talk about the convolutional neural network. But first, let's talk about the generic architecture of any deep learning model. Any deep learning model has some input and an output. Let's consider a task where our input is an image, and the output of the model tells us whether the input image is trump or not trump. Because we are working with images in this task, we are compelled to use a CNN which is followed by a fully connected layer to give our classification output. Let us denote our input as X and our output as Y. Note, we can mathematically say that Y equals 1 is equivalent to predicting trump and Y equals 0 is equivalent to predicting not trump. On the input side, let us simplify the image such that it is grayscale with dimensions of 50 pixels by 50 pixels. Then, we can represent X as a matrix of values where each position in the matrix corresponds to the intensity of the associated pixel. So all pixel intensity values are between 0 and 1, where 1 would be a white pixel and 0 would be a black pixel. Okay, let's dive into the actual architecture of the CNN. To keep it simple, let's stick to a single layer, single channel CNN. As before, the deep learning model we have chosen is a CNN followed by the fully connected layer. The CNN can be split into two stages, a convolution with the kernel, followed by nonlinearity. Okay, so what do we mean by this convolution? The convolution stage takes the input X and outputs the matrix A, that is calculated by the mathematical convolution between the kernel K and X. The kernel matrix can be thought of as the weights matrix of the CNN. The elements of this matrix is what we want to learn during training of the deep learning model. In general, the two-dimensional convolution to find the ith row and the jth column position in matrix A is given by the equation on the screen. More intuitively, we can view the convolution operation as the kernel matrix traversing over the input X matrix. So, for example, the top left value in our A matrix is calculated by placing the kernel matrix on the top of the X matrix in the left corner. Then multiply all overlapping values and add them together to get the corresponding element in the A matrix. Now, by moving K over X, we can continue to compute other elements in A. You may come across many terms when reading up about CNNs, such as padding, pooling, dilation, and stride. So let's start with padding. Padding is fairly self-explanatory, which is where the input image is padded with zeros around the outer edge. The padding can be as thick as one desires. Pooling is where the input image is smoothed or blurred, which means the values at each position are averaged using the surrounding values. There is no restriction on how many pixels are pooled together. So in this example, we can see we just use the neighboring pixels. Dilation is a form of dilution. So in this example, we have a horizontal dilation where the kernel matrix has zeros interleaved between each value. This means the convolution over X will occur over every second value instead of contiguous values. The dilation with zeros can be as wide as one desires too. Finally, the stride dictates the step taken by the kernel matrix over the image X during the convolution operation. In this illustration, we can see the stride is equal to 2. Okay, so let's talk about the nonlinear function f. This is known as an activation function, which come in several different flavors. One common example is the sigmoid function, as shown here. So that's pretty much it for CNNs. In order to get multi-layered CNNs, the blue CNN box can be stacked on top of one another multiple times. And to understand the role of the fully connected layer, do check out our video on deep neural nets. Well, that's it for today, and enjoy!